We're going to study triple integrals in spherical coordinates right now. And again, we should begin by giving a description of spherical coordinates. Once more, as in the case of cylindrical coordinates, we expect to start with a way of assigning to a point numbers that can define its location. And here's how it's done. So imagine that you have a point in a 3D system, that in a 3D space that comes already equipped with its Cartesian coordinates, so like so. And here's what you do. The first coordinate is actually pretty simple. It's the distance from the origin. And since in the context of 3 dimensions, we have already called the distance of the projection to the xy plane from the origin r, in the case of cylindrical coordinates, we have a different letter for this case, which is the letter rho. Okay, so it's the Greek letter rho, and that's the distance from the origin. And the second spherical coordinate is actually one that we already know. It's the angle theta. So to find the angle theta, you can project the point onto the xy plane. So if the point was, let's say, ABC, then its projection is simply going to be AB, 0. And I'm not going to use the coordinates ABC for anything else in this description. And the angle theta is going to be the angle with a positive z, with a positive x-axis. And now so theta, okay, so let's write how this letter is pronounced. It's same as the cylindrical coordinate, same as cylindrical theta. And for that reason, we keep the same notation so that so that there is no ambiguity. Now, let's take a look at the most interesting of the 3 spherical coordinates, which is the angle phi. Here's the angle phi. So the angle phi is the angle between the radial segment, the one, in other words, that connects the point to the origin, and the positive z-axis. And this may be the most interesting of all spherical coordinate. And let's see how this works. Actually, this kind of interesting. To understand how this works, it might actually be a good idea to work on a 2-dimensional plane that contains the z-axis. So, you know what? Let's work on the zy plane. Okay, so this is the zy plane. So everything that I'm going to show you takes place in this plane right now, but it could be pretty much done with any other such plane. So imagine that you have this point, right? So we just said that the angle phi is this one. And what is interesting is what happens as this point turns around. So if the point was on the z-axis itself, on the positive z-axis itself, then here phi would be 0, because the angle between the radial segment and the positive z-axis would degenerate to a 0 angle. Then as you start going in this direction, the angle starts increasing, and when you actually hit the positive y-axis, the angle becomes pi over 2, 90 degrees, right? So it's this angle here. Okay, so everything looks pretty straightforward so far. And then you keep going, And let's say here, when you have this angle on the bisector of the fourth quadrant, the angle, let's say here, becomes 3 pi, no, what would be that? 3 pi over 4, right? And eventually, when you hit the negative z-axis, the angle is pi, right? Because you have this angle right here. Now, here comes the interesting thing, which the only reason it's interesting is because it's different from the cylindrical, from the angle theta. In the case of the angle theta, you keep going. Now, my angle would increase, right? But in the case of the angle phi, that's not what happens, because now once you're, let's say here's your point, instead of measuring this angle and saying that it's an angle over pi, what you're measuring actually is this angle. So in other words, the moment you hit the negative z-axis and then continue, the angles start decreasing again. So in other words, the angle never exceeds pi. So we could have actually defined that from the very beginning as the smallest angle right here, when I said the angle between the radial segment and the positive z-axis. So for example, when you're here, okay, you could do what? You could have measured this angle, right? Or you could have measured this angle and use it as your phi, but it will always be the smallest one. So the correct one will be this one. So as a result, the angle phi is between 0 and pi. And you know that it's 0 when you are on the positive z-axis. You know it's pi when you are on the negative z-axis. And then you have everything in between. So let's do a quick rotation in order to see how this goes. So here you have phi equals 0, right? Here at the bisector, you will have phi equals pi over 4. Here, you will have phi equals pi over 2, right angle. Here, you will have phi equals 3 pi over 4. Then you hit phi equals pi right here, and then you start coming back. So right here, it's going to be again phi equals 3 pi over 4. Why? Because you're measuring this angle. Then here, it's going to be phi is equal to pi over 2, because you're measuring this angle. Here, you're going to have phi is equal to pi over 4, because again, you're measuring this angle. And finally, you come back to phi equals 0. So this is a quick going around the system of coordinates in this direction with pi over 4 stops. Okay, so now that we saw how this angle works, we need to do the usual work, meaning what do we need? We need to define or to give the transition formulas between Cartesian coordinates and spherical coordinates. So let's do that. Okay, so the idea here, and actually we might want to keep this as a useful formula, is that when you have a point, remember, you projected, again, let me just say that this is the point, let's say ABC, I projected to AB0, and the distance of the projection here is R, right? And you can find this projection again right here. So this is also R. And so this little triangle, actually this angle here is going to be a right angle. and you have the distance from the origin that we called rho, and all of a sudden you have this interesting triangle where this angle is phi, right? So what happens is you can do trigonometry on this triangle, and it will be that the sine of the angle phi will be the opposite right side, which is r, divided by the hypotenuse, which is rho. Okay, so this will give you that r, the r of cylindrical coordinates is rho times sine phi. And this is a very useful formula to remember, because if you remember this formula, then finding the transitions from cylindrical coordinate, I'm sorry, from Cartesian coordinates to spherical coordinates and vice versa is very straightforward. Because look, I know that in cylindrical coordinates, x is r cosine theta, right? So here, my r is already known to be rho sine phi. So guess what it's going to be? X is going to be rho sine phi cosine theta. In exactly the same way, y is going to be rho sine phi sine theta. And finally, z can be found again by trigonometry on the same triangle, because here's your z, right? So z is going to be simply rho cosine phi. And these are the transition formulas, and I should add to them that x squared plus y squared plus z squared is equal to rho squared. Okay. So these formulas are going to help us to go from to express a function that is given in terms of Cartesian coordinates to express it in terms of spherical coordinates. And finally, we have the Jacobian, right? Here, the Jacobian is going to be much more interesting. And it turns out that the Jacobian is rho squared times sine phi. And that's it. Okay. So I think we have everything that we need here. And it's time for an example. Okay, so let's do an example. So compute the triple integral of x dv over u, where u is the part of the unit ball that lies in the first octant. Again, the first octant is defined by the conditions that x greater than 0, y is greater than 0, and z is greater than 0. Okay, so let's try to actually sketch it. So we have the boundary of the ball is the sphere, and we're just interested in what is going on here in the first octant. Okay, that's the best I can do in terms of a picture here. What is more important is to write this domain to see what this domain is going to look like. So it will be all the rho thetas and phis, such that rho is between 0 and 1. Theta, since when you project the first octant onto the xy plane, you get the first quadrant. It's going to be from 0 to pi over 2. And phi is going to be, if you think about it, try to remember the picture that we showed before, the a progressive rotation on the zy plane, that will be from also 0 to pi over 2. So that's our domain. So it's a box in spherical coordinates. And let's look at our integral. So we will have x dv over u. And let's write it as an iterated integral. So it should be pretty straightforward given that this is a box. So let's match them. So we have d rho from 0 to 1. We have d theta from 0 to pi over 2. And we have d phi from 0 to pi over 2. That's step 1. Step 2 is to take care of the integrand. This is where we have to remember our formulas. We have x, so x is rho sine phi cosine theta. And finally, we should multiply by the Jacobian, which is rho square sine phi. And now, of course, this integral splits. It's an interesting integral. So we will have the integral from 0 to 1 of rho cubed d rho. Let me see if I can fit everything here without changing page. We'll find out in a second. Then we have the integral from 0 to pi over 2 of cosine theta d theta. And finally, we have the integral from 0 to pi over 2 of sine square of phi d phi. Okay, so let me change color so that there is some distinction of this computation. So what do we have here? The antiderivative of rho cubed is rho to the 4th over 4 from 0 to 1, which gives us 1/4, right? Okay. The integral of cosine can be found by using the fact that the antiderivative of cosine is sine. So you have sine of pi over 2, which is 1, minus sine of 0, which is 0. So that will give you 1. Now, this integral is a little more interesting. Again, I'm going to go to my double angle formula. Cosine of 2 phi is cosine square of phi minus sine square of phi. Use the Pythagorean theorem, and this will be 1 minus 2 sine square of phi. And now solve for sine square of phi, and you will get sine square of phi is equal to 1 minus cosine of 2 phi divided by 2, which means that if I want to take the antiderivative for this integral, the antiderivative is going to be phi over 2 minus sine of 2 phi over 4. And again, we have a situation that we encountered before. It's actually quite agreeable for us. We want to take this from 0 to pi over 2. If you plug in pi over 2 in sine of 2 phi, you will get, or 0, you will get sine of pi and sine of 0 respectively, both of them being 0. There is no contribution of the second term to the integral. The only thing you get is from the first term, which actually will give you pi over 4. So now you have the three things that you need to multiply together. So it's 1/4, 1, and pi over 4. And this is going to turn out to be pi over 16. A very interesting computation. And again, the formulas that happen to be a little more complicated than all the other sets of coordinates, or integration in all other sets of coordinates that we have seen, make the whole thing a little more interesting. But I think it would also be a good idea to do the volume of the ball of radius r. Remember, we did that using cylindrical coordinates. Now, spherical coordinates are so much more intimately connected with the geometry of the sphere that, guess what? When we switch into them, we're going to get a box, and the computation is going to be much more agreeable. So as our next example, use integration in spherical coordinates compute the volume of the sphere. Not of the sphere. I keep saying that the sphere is actually the bounding surface of the ball of radius R uppercase. Again, I'm not so sure how much a picture helps here. I mean, we can all visualize the ball, and my ball is not especially pretty here, but in any case, we can so the radius is R. We can express this in spherical coordinates, and this is going to be rho, theta, and phi. And rho, it goes from 0 to the radius of the ball. Theta, you're going all around. And as for phi, you still have the full range. So phi is between 0 and pi. It's so nice. It's the bugs I was just talking about. And since I want to compute the volume, that means that I need to integrate the function 1 over u. So when I turn to spherical coordinates, I will have d rho gets matched with 0 to r. D theta gets matched with 0 to 2 pi. And d phi gets matched with 0 to pi. The function that we're integrating, as we said, is the function 1. So that's step 2 of the process of turning the integral into an integral in spherical coordinates. And the Jacobian is rho squared times sine phi. This integral splits. So we will have the integral from 0 to r, rho squared d rho, times the integral from 0 to 2 pi d theta, times the integral from 0 to pi of sine phi d phi. And this is going to be what? So all of these integrations are quite simple. So here you will have rho cubed over 3 from 0 to r, which gives you rho cubed over r cubed over 3. And here you will have just 2 pi. And this is also a very simple one. The antiderivative is negative cosine phi. You want to go from 0 to pi. This gives you negative 1, which is 1 minus negative 1, which is another plus 1. So this is going to be 2. Put them all together, and you will have r cubed over 3 times 2 pi times 2, which is 4 pi r cubed over 3. That's precisely the result that we found by using integration in cylindrical coordinates. And of course, that's the well-known formula for the volume of the ball. And that's it. Okay, so we can see that the integration was very, very smooth here. Let's do a couple more examples. I think spherical coordinates is precisely the set of coordinates in which we have to practice most. Cylindrical coordinates are quite reminiscent of and quite similar to polar coordinates, but in spherical coordinates we have this angle phi that makes things always much more interesting. So let's look at the following example. So compute the triple integral of z dv over u, where u is the region of space between the spheres x squared plus y squared plus z squared is equal to 1, and x squared plus y squared plus z squared is equal to 4, for which, and now we're going to really define an octant by giving the different coordinates. So let's say x is less than 0, y is greater than 0, and z is less than 0. Okay, so how do we deal with this integral? Okay, now how do we understand how this is located? I mean, it's not that we really need that information, as we're going to see, but let's at least make an effort. So here we want y to be less than 0, y to be greater than 0, and x to be less than 0, which means that it's located somewhere in the back here. And since z is less than 0, it's this region that is not the one in front of us, it's the one behind us. Like I said, I'm not sure the picture is going to help that much. There will be a very simple way of actually describing this domain. So this domain is all the rho thetas and phis, and let's do this carefully. So rho, you're between these two spheres, and rho is going to be between 1 and 2, because the first sphere has radius 1, the second sphere has radius 2, and you're right in between. And theta, what is theta going to be? In order to understand what theta is going to be, we'd better sketch the xy plane and try to identify the region that these two inequalities define. So x is less than 0 and y is greater than 0, which means you're right here. And this means that theta is going to be between pi over 2 and pi. And finally, where is phi is going to be? Well, again, you might want to draw the YZ plane and realize that we're down here, where obviously phi here is pi over 2, and then you go all the way to here where phi is pi. So phi is going to be between pi over 2 and pi. And this is our domain, right? Once we have the domain, then the rest should be quite straightforward. However, let's do everything. So we're going to put the integral together. So the triple integral of c dv over u is going to be, so we match d rho with 1 to 2. We match d theta with pi over 2 to pi. And we match d phi with pi over 2 to pi. That's step 1. The integrand is z, and we said already what z was, so z is rho times cosine phi. And finally, our Jacobian, step 3, is rho squared times sine phi. Again, this integral will split, so we will have the integral from 1 to 2 of rho cubed d rho times the integral from pi over 2 to pi. Well, you don't see any explicit mention of theta here, so you might as well take the function 1, d theta, and finally the integral from pi over 2 to pi of cosine phi times sine phi d phi. Okay, so the first integral will be rho to the 4th over 4 from 1 to 2. That will give you 16 minus 115 over 4. The second integral is just the length of the interval, so this is going to be pi over 2. And the last one is a little more interesting, but quite straightforward. We can do a substitution. U is equal to sine phi. Du is equal to cosine phi d phi. And we will get the integral of u du. Now we have to be careful with the endpoints. So what we're supposed to do is take the endpoints and plug them into the substitution. So take pi over 2 and plug it into sine. What do you find? Sine of pi over 2. What is sine of pi over 2? 1. And then take the number pi and plug it into sine phi again. You get sine of pi, which is 0. So that's what you get right here. And of course, this is going to be u squared over 2 from 1 to 0, which is going to give you negative 1/2. Negative. This is where once you do this for the first time, you look at it and you're like, why negative? Whoa, what's going on here? Because it turns out that if we put everything together now, this integral should be negative 15 over 16 times pi, right? I mean, if you multiply these three numbers together, and at first, there is some surprise here. Why did we find a negative number? I mean, this looked like a very civilized integral up here, right? But then you have to think a little more carefully, because what you had here was the function z, right? And what was the domain implying about z? That z was negative, right? So the integrand was negative. So it only makes sense that we find the negative integral. We should have been worried if we actually found the positive integral here, then we knew something would have been off, but finding a negative integral is precisely what anybody would expect. And so it makes perfect sense here. Okay, let's see. Let's do one more example. Let's make this a volume example. And let's compute the following. So look, start with a sphere. Let's say that the sphere has radius 2. So let's say that the sphere has radius 2, and then cut it with this cone. And create this little thing that looks like an ice cream cone to me. Not everybody agrees with me here. There are some funny stories here, but regardless, this is what we get. So let's call this U. And we would like to find what is the volume of U. Of course, what I haven't told you is I told you that the sphere had radius 2, and I need to tell you about the angle. Which angle? Let me try to identify what angle needs to be identified here. It's precisely this angle right here, the angle of the cone that we're using. And let's say that this angle is pi over 6. Okay, so let's see first of all what U would be. So it turns out that U is quite nice, has a very nice description. It's all r thetas and phis. So rho will be between 0 and no, there's no pi here, sorry, 0 and 2. Nothing strange is going on here. And theta, since you're going all around, theta is a no-brainer here. It will be between 0 and 2 pi. And where is phi? Again, to understand where phi is, sometimes it's a good idea to draw the YZ plane. And you can clearly see that it's cut out by an angle which is pi over 6. So you can see that you go from here where phi is 0 all the way to this point where phi is pi over 6. So shouldn't be a big surprise that phi is between 0 and pi over 6. Okay. And that makes it quite straightforward. So now the volume of u is going to be the triple integral over u of the function 1. And now let's write it as an iterated integral. Let's match d rho with 0 to 2. Let's match d theta with 0 to pi. And finally, let's match phi with 0 to pi over 6. The integrand is simply the function 1, and we need to multiply with rho squared times sine phi. And this is going to be, it splits again. So integral from 0 to 2 d rho. We're integrating rho squared here. And then we have the integral from 0 to 2 pi. We don't have an explicit mention, an explicit occurrence of theta in our integral. So this will be from 0 to pi d theta. And finally, we have from 0 to pi over 6 of sine phi d phi. Okay, let's compute this integral. So we will have rho cubed over 3 from 0 to 2. That is going to be 8/3. Then we have the integral of the function 1 from 0 to 2 pi. That gives you 2 pi. And finally, you have sine of phi, and you need to go from, the antiderivative is negative cosine of phi, and you need to go from 0 to pi over 6. Put pi over 6. That will give you cosine of pi over 6, which is square root of 3 over 2, with a negative sign, of course, in front. And then you need minus, and you will have negative cosine of 0. Cosine of 0 is 1, so negative 1, which will give you 1 minus 1 minus square root of 3 over 2. If you clear denominators, that's 2 minus square root of 3 over 2. So we have these three numbers to multiply together, and that is going to give you what? The 2 from 2 pi and the 2 in the denominator will cancel each other, so you will get 8 times 2 minus square root of 3 times pi over, and the sole denominator that remains here is that 3. And that's it. That's the volume of our ice cream cone. And this completes our examples of integration in spherical coordinates. I hope you enjoyed it. It's quite fun. And thanks for watching.